Hello, okay. Um, so let's start. So today is going to be the last topic before our midterm exam, which is next week. The midterm will start at 8:30, so like 30 minutes before our usual time. So you have full 3 hours. You can bring physical copy of note, textbook, anything that you write, but it has to be in paper format. Um, you can also bring calculator. It's not mandatory, but if you are not sure about your calculation, you can bring calculator. And the topic cover will be from the first week to this week. Yes. Normal calculator is fine. Yeah. Okay. So today, our topic is about ranking. So we learn clustering, we learn decision tree, we learn linear regression. Um, Today, we learn about new type of problem called ranking problem. And this problem actually come up a lot in the past 10 years. One of the most uh, commonly application is Google search, right? You search a keyword and it will give you a list of uh, pages. And the task is to rank which page would be the most relevant to your query. So we will look at how can we define this problem mathematically, and then we will look at some of the learning method. Um, some of them are quite old, but it's very easy to understand. Today, the method for ranking problem is very complex, and I will show you some improvement idea from learning method. So for ranking problems, right, you have a query, right? You have a query, and you want to return a relevant item, right? For example, in a search engine, you type in your keyword, and then it will give you a list of pages. Or new feed, right? When you open like social media, and it's gonna recommend you some of the posts, maybe from your follower, maybe from someone you never know before, but they think that this post would be related to you. So the query in this uh, case, it may not be the keyword that you search, but it may be your profile. Like your profile can be the query. So how can we solve all of this problem? Um, so we learn linear regression, we learn clustering, we learn uh, decision tree, right? And all of this that we learn cannot answer all this problem directly. So in computer science, it's very common that when we have our background knowledge, right? We have our background knowledge, and then when we see a new problem, what we want to do, we want to transform the new problem so that it can be solved with our background knowledge. And we will try to do it like this in the first half. So the ranking problem, we can frame it as information retrieval problem. And in information retrieval problem, we have item, which is maybe document, and then document is consists of word, right? So basically, in Google search, the item would be the HTML page, and the word in HTML page is going to be the word here, right? And query, right? The keyword that you search is also consists of word. So there are some similarity between the words in the query and the word in the document. And in information retrieval, they would match word by word, right? If your query have this word and the document have the same word, then they would have a higher score, right? And then they would have a lot of heuristic function, right? If let's say I have the word cat, right, in the query, and then document have like 10 cat, the word 10 cat, and then another have 20 cat. So maybe the document with 20 cat would be more relevant to your query, right? So this is what information retrieval does, right? It matches the information from the query to the document. And the difficulty for this is that this based on purely the word that the user search. It doesn't understand the intention or understand the sentence at all. It just matches the word in the sentence. And this is actually not learning, right? It's not learning because if you only just match word from query to document, right? You only did the analysis, right? What is your data? You do not need, you actually don't need the data, right? You can think that, okay, the data is maybe the document, right? You have a database of document, but you didn't process anything, right? You didn't actually have a parameter, right? So for information retrieval, well, you just did everything based on um, some assumption, right? You don't have you don't have actual data, right? For example, you don't know that maybe this query match to this particular document more than another document, right? You just assume that document with more word relevant to your query is more likely that it will be relevant to the query that you asked. So how can we acquire the label? So what is the label in this case, right? So the label in this case, right, we have item, we have document, we have query. What is the label, right? So the label in machine learning sense is the correct answer, right? What we need correct answer. So in the ranking problem, what is the correct answer? Right? So when you think of a correct answer, right, you're gonna have some, right, for classification, okay, for example, for classification, right? Right, you have, let's say you have an image, right? And then you identify it as cat. So the cat is the label, right? This data correspond to this class, right? So that is the the label. But for here, what do we have? We have query, and then we have document, right? So for this pair, what do we get? What should we get? What should be the label, right? I have this particular query, and then I just pick one document from my database, and this pair, right, is basically the image, is equivalent to the image in the classification. What should be the label? What do you think should be the label? So the label can be like many patterns. If it's a binary, right? In binary, it can mean maybe 0 mean not relevant, and 1 mean relevant, right? So we can match this query to all the document. And if this document is relevant, then this pair, you have a label of 1. And if this document is not relevant to the query, then you give it a 0. So basically this pair, right, this pair of query and document is become our feature, our data, right? And the label would be the indicator whether these two are related or not. There can also be, hello, test, test. I think microphone is, okay, it's back. So this is a binary. We can also have like category. What should be the category for this? Right, the category could be the score. Like for example, you can have like 0 mean not relevant, and then 3 would be the most relevant. So you can have the level of relevant, right? Right. And then you can also have some kind of like a real value, right? Basically a relevant score, right? You can give a score for this particular pair. So in the information retrieval problem, we don't actually have the label, right? It's just that we don't use the label. But for us in machine learning, we need it, right? Because we want to learn something. So how can we obtain a label, right? So we can use human, right? We can use human to rank each query pair, right? The query and document pair. And if you have like, let's say 1,000 document, and then you have like 1,000 query, you would have like 1,000,000 pair, right? And so that become quite a task to accomplish. So in most database, in most benchmark database for ranking problem, not, I think most of the database is not from manual labeling. Most of them come from automatic. And this using the click-through, right? So the click-through, what is click-through, right? So basically, in Yahoo, in Google, right, you search, and then it gives you a list of pages. And then whatever link you click, it's gonna record the click, right? So this query, this page, and then you click. So it's basically this query and document pair, the label would be 1 because you click, right? So this is the click-through, right? So I think one of the very first ranking benchmark is actually from Yahoo, and it actually used the result from search, right? The user search in Yahoo, and then when whatever you click, it's gonna record, and then it's gonna comply with the data set. So now our data have the query pair, right? The query document pair, and then we have a label. So the next question is, how should we define it better, right? Because before, what we have, right? We have feature, right? We have feature, and then we have target, right? We have feature and target. Right now we have target, right? We have a label, right? So this one, the document score, right? For document I with the QD1, whatever the score gonna be. So our training data is gonna have a set of query and a set of document. And then some of the data set is gonna have this pair, right? The document related to QI. So this is a set, right? A set based on the index I. So D is just the set of all the document. And if you subscript I, it's gonna be a subset of D, and the member in the set will be related to the query I. And then the same index, you are going to have the score, right? In this case, it can be binary, it can be relevant score. And then when you want to predict something, you would give a new query, right? And then you want to output a list of relevant documents. And depending on the method you use, and also how you define the score, some of the measurement only care about whatever you return is relevant to the query or not in any particular order. Some of the metrics will actually consider the ordering of the item, right? And then we will see which metric will cater which case. So there are many types of the ranking problems. Basically, there are many ways to solve the ranking problem. The first way is called a pointwise. So a pointwise, you look at query document pair. You only look at one pair, and then you have the score, right? You have the score. And your task is to learn the score, right? So one data set is 1 point, like one query document pair is 1 point, and then you want to learn the score. And you can learn this using a regression or a classification, right? Basically, you have query document pair, and then you convert it to a feature vector, right? And then you have your label is going to be the target, right? And then you want to learn this function using regression. So if the relevant score is a real value, then you use regression. If it's a level of relevance, mean that it's a discrete value like 0, 1, 2, 3, then you can use classification to classify which pair of query document belong to which class of relevant. So for pointwise, it's nothing new. We can use our previous knowledge to solve this. The more interesting part is that we can do a little bit more, right? Because in the ranking problem, sometimes we care about the order, right? We care that this document is more important than another document. So we have a pairwise approach, and a pairwise approach is actually you have query, right? You have query, and then you compare two documents, right? You compare two documents, and then you say which one is better. Right, so this is a pairwise. Right, you compare two documents at a time, and then you pick which one is better. And for the prediction, right? For the prediction, you would have to pick a pair of documents. And then whichever one is better, you return the better one. Right? So the pairwise is actually like learning a comparison function, basically. Right? You compare document 1 to document 2. And if you give like a positive number, it could be that the document 1 is better. If it's a negative number, the document 2 is better. And so when you return a list, you would want the better one to be higher up on the list. So this is pairwise. The more restricted one is the listwise. The listwise actually care for the entire list, right? So for one query, your algorithm have to return a list of document. It's going to have, you have to return a list of document. And based on the ranking of the document, you will give some score, right? And in the most case, right, the list wise, you can think of it as many point wise. If you can learn the score for each document pair, you can predict the entire list in your database, and then you can sort it by the score, by the relevant score from your prediction, right? So that is like one way that you can use point-wise for list-wise. But for some advanced algorithms, it's going to have a network that actually do the ranking for you. Basically, you send in maybe 4 or 5 documents, and it's going to score 5 of them at the same time. So that is the ultimate goal, right? Basically, this is the most advanced, and it's still ongoing research for the list-wise approach, right? So point-wise is like the very first, maybe 5 years of the ranking problem, and then we move to pairwise, and now we are in the list-wise territory. So what are the popular methods, right? So for point-wise, we actually already learned all of the technique, right? We can use linear regression, we can use decision tree, we can use logistic regression. And for pairwise, we have RankNet, we have SVM rank, and actually there are many more algorithms. For list-wise, all of them would come from neural network, right? Because the list-wise, you have to incorporate a very complex structure, right? So you have like ListNet, maybe Lambda Mart. I think these two are like the most common one. For us, we are going to learn pairwise, right? And then look a little bit into a listwise. So let's start from the pointwise, right? So in the pointwise approach, for each query pair, you want to give a score, right? You want to give a score. And if you want to use like linear regression, decision tree, and so on, you have to convert query document into a feature vector, right? You want to create it into a feature vector. So how can we calculate? How can we transform this query document into a feature vector? So there are many ways to convert it. Some of the data set already convert it for you. But if you want to use your own data set, you will have to learn how to construct a feature vector for your particular data set. So we are going to learn three ways of converting the query document into a feature vector, right? Each one of these will give you one number, right? All of these will give you one number. And in the actual data set, in the benchmark data set, they use this score with like other score. So you can mix and match, right? You can combine many score to construct a feature vector, right? And then you can train, and then you can rank based on the output value. So this the training the training phase and then the ranking phase is quite simple because we have already learned. So we will look at how can we convert the query document into a feature vector. So let's start with page rank. So page rank, this algorithm is used by Google search. And in 2019, all the patent expire, so other company can use the PageRank. So before 2019, no one can use the PageRank algorithm because it was patented by Google. So the key idea for PageRank, so for the PageRank, it doesn't take the query into account, right? The PageRank will just score the document inside the database itself. So the key idea for PageRank is that more important websites are likely to receive more links from the author. So in the website, right, you have a web page. And in the web page, you will have link to another page. So basically, it's a link, right? It's a link network. And the key idea is that if there are many websites linked to the same page, like let's say there are like 1,000 websites that have a link to this particular page. So it means that this page must be very important because everyone keep referring to it, right? This also work in a research paper, right? Basically, the most cited research paper would be the most important, right? Because everyone just cite this particular paper. So it's the same concept. And based on this concept, they introduced the algorithm to compute the page rank, the score for each of the page. And the key idea is that initially each page have a score of 1, and then it will distribute this score to all the pages that it points to, right? For example, at the start, everyone have 1 point, right? So in the first iteration, this page point to this page twice. So maybe it just split the score to like 0.5, and then it gives this to 0.5. And then this one doesn't point to anything, it's gonna keep all the score, right? So it's 0.5 to here, 0.5 to here, right? And then this one will become 1.5, this one will become 1.5. But this page also point to another page. So it's gonna reduce the score to become 1, and then this one add 0.5 to 2, something like this. So it's try to distribute the score from ourselves to the neighborhood. And we usually have the equation for this, right? So the PR, here is a page rank score for page P is equal to 1 minus D over N plus D times the sum of the PRI divided by LI. So what are all of these numbers, right? So we start with the first number. So 1 minus D over N. So what is 1 minus D over N? So right now, D is the damping factor, right? So what is the damping factor? So the damping factor is the percentage of how much the score you are willing to distribute to the neighbor. So if I have a damping score of 0.85, so what I mean is that if at the start my score is 1, right? If at the start my score is 1, I will keep 0.15 to myself, and then I will distribute 0.85 to all of the page that I link to, right? So this is the damping factor. And here, L is the number of outbound link. So basically, all the page that I point to, I will distribute them equally. So the equation here is the so they work out the equation at the end. But if you want to do it by hand, it's better to do the distribution instead of using the actual equation, right? So, for example, at the start, I have all these pages, right? I have all these A, B, C, D, and the arrow mean that this page have a link to another page. So at the start, A, B, C, D have a score of 1, right? Have a score of 1. So using a damping factor, right? So each page, so this one you will get 0.15, right? Over n. N is the number of page, right? Yeah, it's the number of page. So everyone will get this much score, right? Right, this is the start, right? And then each one of them will get extra score from whatever page that it point to. So for example, in page A, right? In page A, there are 3 inbound, right? So there are 3 inbound. So A will get the score from B, C, and D, right? From B, C, and D. So basically, this one, right? So you have B, C, and D, right? So in the initial score is 1, right? So you get 1 plus 1 plus 1, right? And then it's divided by the Li, which is the number of outbound link. So A have only 1 outbound, so it's divided by 1. Right? So this is the score of the page A after the first iteration. For B, right? For B, there are only 1 inbound link, right? So you only have 1, and B have 2 outbound link, so it's 1 over 2, right? So this is the score for page B at the end of the first iteration. And you keep repeating this over many iterations, it will eventually converge, meaning that like all the score will become a constant. Like it will have a very small change from one iteration to another iteration, so you can stop there. All right. So the page rank will actually give basically it just rank the page in the database, right? Without query knowledge. So page rank doesn't use any query. It just uses only document and then give the score. And this score can just be one of the feature in your query document pair when you do feature extraction. And then we have TF-IDF is another score. So for TF-IDF, this one use both query and document, right? So you use both pair. So have you heard of TF-IDF before? No. TF-IDF basically is try to count the number of occurrence of the word, right? So we have TF, which stand for term frequency. So the term frequency is defined on the term T and then the document D. And the formula is very simple. Basically, you count how many words appear in the document divided by the number of words in the document, right? And if you have many keywords, you can do the average TF as well. But this one I only use one word, right? One word. You count the number of words in document, and then you divide it by the number of words, right? So basically, it's the frequency of word in that document, right? So TF. So mostly this T will come from the query, and then this D is from the document. Right? So this is the TF. And then we have inverse document frequency, right? So in the term frequency, the intuition behind it is that if the word appear more in this document, it should be more relevant, right? So that is the information retrieval knowledge that we have, right? That is the TF. But maybe this particular word is very common, right? If this word is very common in all the document, maybe this word is not that important. So we have inverse document frequency. And the inverse document frequency will measure how important a word is. And this particular score, it actually define on the keyword, right? Define on the term from the query, and this will count of all document, right? Basically, this one is the number of all the document. The bottom is the number of documents that this word appear, right? So we have right. So let's say we have D1, D2, D3, D4, and then we have this term. And if this term appear in 3 or document, then you will get the log 4/3, right? So we have 4 documents, and this particular term appear only in 3, so you have 4/3, right? So basically, just count the number of documents. And when you take the log, right? You take the log. So what happened here, right, is that what is the maximum value of the IDF? What is the maximum value of IDF? So the top one is fixed, right? Right. The number of document is fixed. So the varying variable is the bottom, right? And then the bottom what are the range of the value from the bottom? It could range from 0 to the number of document, right? So we have uh, D at the top, right? And then in the bottom, we have 0 all the way to D, right? And because we cannot divide by 0, right? Sometimes they will just add 1 at the bottom so that, you can divide non-zero. But if, let's say, this is 1, right? The number is 1. So this fraction, you get D, right? And this fraction, you get 1. And which one is bigger? What is log 1? Log 1 is 0, right? And then log D is going to be the number is greater than 0, right? So if it's 1, right, you get this score to be 0. It means that this word is not important. So what kind of word that is not important is the word that appear in all of the document, right? If this word appear in all document, you should not consider it because it doesn't tell you which document is better, right? It's everywhere. Everyone use it, right? And most of the time, um, this word that will give you log of 1 would be article or um, preposition, right? For example, a and the, maybe in, the be on, right? So the word that is not a noun phrase, basically, right? It's an article word, right? All these words will give the score of 0, so you should not consider it. But for other words, right, that appear in smaller subset of document, it should be important. And the final score, right, you just multiply TF and IDF. So let's do an example, right? So I have this 3 document. It's very short sentence, right? The sky is blue, the sun is bright, the sun in the sky is bright. And my query is bright, right? So I want to calculate the TF-IDF score. So the way that I had to calculate, right? So I have the TF score, right? My query, I only have one query, right? So it's going to be bright. And then my document, I have 1, 2, 3. I have 3 documents, right? So I want to compute the TF for each of them. So what is my TF score for bright and document 1? What is the score? 0, right? Because the word bright does not appear in that document, so you get 0. What about document 2? What is your TF score? It's 1/4, right? It appears once, and your document have 4 words, right? So it's 1/4. What about 3? It's 1 over. How many words are there? 1, 2, 3, 4, 5, 6, 7. Right. So it's 1/7. Right. So that is the TF score. What is the IDF of bright? What is the IDF of bright? How many documents we have? We have 3 documents, right? So the top would be 3. How many documents that the word right appear? 2, right? Document 2 and 3. So you have 3 over 2, right? So you have, so the TF IDF for Bright and document 1, right? It's going to be 0. For document 2, it's going to be 1 over 4 times log 1.5. And for doc number 3, you will get 1 over 7 log 1.5. So which one have the highest score? Is it doc 1, doc 2, or doc 3? Which one have the highest score? 2, right? Right. So not only because like both of these had the word bright appear once, but the document 2 is shorter. So the word become more important, right? Because if you have a long document, it's more likely that your word will appear in the document. That's why the TF score will try to discount by dividing by the number of words in the document. Right? So if we only use the TF IDF score to rank the document, it's going to be document 2 followed by document 3 followed by document 1. Right? You can just use the score directly. But for us, this is just one feature, right? One number in the feature vector. So far, so good. Should be able to calculate all of this, right? So in the exam, if it ever appear, you can just write it like this. You don't have to, you don't have to get the decimal answer. You can just answer it like this. Like you don't have to take the log and so on. And it's easier to grade in this format because I know that you substitute the value correctly. If you multiply out to be some number, then I don't know where you put it wrong. So I may not be able to give you a partial credit. And then we have BM25. Now the BM25 is actually a fancier version of TF-IDF, right? So for us, we have TF-IDF, right? The TF-IDF is it's just a multiplication of TF-IDF. But for BM25, right, the TF part become a little bit more complicated. And how can we describe this? How can we explain the new equation for the TF side? So the TF side, you have K, like you have K1 plus 1, right? So on the top, basically, what you have is TF plus K1 times TF, right? Right. And the front part, right, this TF and this TF is the same, right? So what are we comparing? We're comparing the original TF with this new equation. So what is this new equation, right? 1 minus B plus B times D divided by average DL. So what happened in this case is that not only that you count the number of words, right? So in the original TF, you divide it by the number of words in the document, right? And so for a document that have a long a longer length, it will have a lower TF score by default. And so what it does is it tries to compensate by, instead of dividing by um, the number of documents, it will discount by the average document length. Right, so it's basically just more normalized version of the TF. Right, you use the average document length, basically the length of all document, you sum up and then you take the average, right, and then you divide it by D, right, and then you have 1 minus B, and B, that would be like a weighted, right, because it's sum to 1, right, 1 minus B and B sum to 1, and so you can pick B to be any number between 0 and 1. The most common value would be B to be 0.75, and then for K, it's going to be between 1.5 and 2. Right. So this is the BM25. And as you can see, right, it's actually sum, right? It had a sum in the front. So in TF-IDF, I only show you that only one word, right? One keyword. What is the score for this particular one keyword? But let's say my query have two words, right? For example, my query become bison. Then basically you compute again the BM25 or TF-IDF for each word, and then you can sum it up, right? So you have TF-IDF for bright, you have TF-IDF for sun, and then you sum up for each of the document. So that is where the summation come from. So what if I have maybe only one document, and then for this query, right? How can I compute the BM25? So for the BM25, I also have to compute the TF and then IDF, right? So for here, I will have to compute for two keywords, right? For the word quick and the word fox, right? And because I only have one document, right? The TF for this is 1/4 for both cases, and then IDF is both I think it's both 0, right? Right, because 1/1, I only have one document. So for one document, it doesn't help that much. But let's say I have many documents and I want to just focus on one document. So my IDF score would be some number, right? Let's say it just be let's say it's X, right? X, because for the BM25, the IDF is untouched. The only difference is the TF part, right? So what I will have is I will have the like K1 plus 1 times the TF, which is 1/4, right? And then I will have the 1/4 on this side, and then times the K1, right? And then if I pick the B to be 0.75, then I will get 1.25 plus 1.75 times the number of documents, right, divided by the average document length, right? So this is going to be the BM25 for the word quick for the word quick, and then the fox would be the same formula, and then you just time 2, right? So time 2 would be quick plus fox. So this is how you calculate the BM25 score. So we have at least 3 ways to convert the query document pair to a feature vectors. And for the pointwise, we can use linear regression or a decision tree. And now we are moving toward to the pairwise, right? So let's say I have the feature for each document pair ready, and I want to learn the score, but in a pairwise manner. So in a pairwise manner, right, we are going to use something called SVM, support vector machine. And the support vector machine is an optimization. It's going to minimize this weight, right? And this um, the select variable. So what it does is that you have the point that are in two class. So basically SVM is for classification, right? And what SVM does is try to find the separating plane between one class to another class. And this optimization will try to maximize, basically to draw a line such that the margin from both class is as large as possible, right? So that is the SVM. So this line is described by the weight W, right? This X, right? This X is our feature vector, right? So if we have a query document pair, right? If we have a query document pair, you convert into a feature vector, right? And then for the class, maybe you can do binary label, like relevant or not relevant. And in ranking SVM, we're going to say that if xi is ranked higher than xj, then we want wxi to be greater than wxj. So basically, this one is the prediction, right? This one is the prediction. You want the prediction value of I to be greater than the prediction of j. So that what it means to be ranked higher. And so what we can do, for each pair xij, right? For each pair xij, we can assign a label 1 or a label 1, a label -1 based on which one should rank above another, right? If xi rank higher than xj, then you will have a label 1. If xi is ranked lower than xj, you will give it a label -1. And if we label it like this, right, it become a classification, right? So your feature, right, your feature is xi and xj combined, right? You put xi and then you put xj and then you concatenate both feature. And this feature will have to be class 1 or to be class -1, right? Based on the ranking. And the beauty of this is that we can we can keep the same number of features by subtracting, right? Subtracting the vector. And the reason behind it is that if xi, right, rank higher than xj, right, you want wxi to be greater than wxj, right? And the label would be number one. You can rewrite this equation to be w xi minus xj greater than 0. And this greater than 0 correspond to 1 very nicely. Right? Basically, we want this to be as close to 1 or maybe greater to 1, greater than 1 as much as possible. And so for our original, right, for example, I have my query, right? They all have the same query. And then I have a feature vector, right? So this could be this query plus document 1, this query plus document 2, this query plus document 3. And in the original database, I only have the relevant score, right? I only have a relevant score. So instead of learning the score, I can transform this dataset to be a pairwise. So my new feature vector is going to be the difference between the feature vector before, and the label is no longer the relevant score, but it will be based on which one have the higher score, right? For example, I have x1, x2, right? x1 have score of 0, x2 have score of 1, so x2 should rank higher than x1. So in my new database, I will have x1 minus x2 as my feature, and I will assign a label of -1, right? Because x2 is ranked higher. And then we only use this new data to learn um, to uh, to train the model. And it's important to note that for the conversion, if let's say x3 also have the score of 0, so x1 and x3 also have the same score, it means that in the new dataset, you are not going to use this pair because it have the same score, so you don't know which one rank higher. So that pair will not appear at the end, right? So the only pair that will appear in the new dataset will be the one with different score, because you can make a distinction which one should rank higher. For the prediction, you actually don't need to convert the test data to be pairwise. You can use the same weight to score each document normally. Right. So the HS formula for this, we are minimizing the same function, but the constraint, we actually make a pair, right? So instead of just xi or xj, we have the difference between xi and xj, and then you say that it's greater than 1 minus the select variable. And we will learn more about SVM in the later half of the course. There will be a topic, the whole topic about SVM. So you don't have to worry about it now. You will learn about it later. But this is how you can do a pairwise just from this relevant score, right? Because if you only have relevant score, you can only use like linear regression, right? But if you want to use classification algorithm, maybe you have to transform the data a little bit so that it fits the classification condition for the problem. What about listwise? Now, for listwise, the problem become more complicated because you are dealing with a list of answer, right? And the hard part is that if we give you two lists, right, list one and list two, how do you compare both lists, right? Is list one better than list two, or are they similar, right? So that is the problem that we have. So for ListNet, right? For ListNet, what it does is that it will try to minimize the difference between two probability distribution. So what do I mean by this? Is that to compute this list, right? So one list would be the ground truth, one list would be from the prediction. They want to have a probabilistic model of how this list is constructed. And the probability of item I being at the top of the list is given by this equation. So we have e to the si. So for each item, you have the score, right? Each item you have the score. And if you want to calculate the property of this particular item to be at number one in the list, right? You would be the e to the si divided by the sum of e to the sj. So they use this to be a representation of the probability distribution. And the loss function, right? Loss function, it will compare P and Q, right? Is a cross entropy. If the property are the same, the loss function would be very close to zero. And if it's far apart, it's going to be have the higher value. So for listeners, it not just use the score to compute, but also like the score for the entire list for the loss function. And the algorithm for the ListNet, right? The neural network is in the middle. What it does is that it have many query, right? It have many query, but for each query document pair, it's gonna fit. It's gonna be the input layer for the neural network, and then it's gonna give you the score. right? So the input here is going to be the query document, going to be the input, right? And then it's going to pass through some network, and then you get the output, right? Basically, it's uh the SJ, right? The score, right? And then instead of comparing this to the original score, like one by one, right? Even a point wise, you'll be just comparing this to the ground truth, right? You have this query document pair, you know the correct score, right? And then you can compare that score directly. That would be point wise because we compare one by one. But for the ListNet, right, you have this SI for all the query pair, and then it try to calculate the distribution, right? Right, it calculate the probability measurement, and then it will do the gradient descent, right? Basically, this is the loss function, right? The loss function is this, right? So basically, it calculate P for each document for the prediction, using SI for the prediction, and calculate Q for SI from the ground truth. And then it's gonna use the gradient descent to minimize the loss function here, right? And then it's gonna keep updating the parameter based on the loss function. So that is the general idea. What are other approaches? So I'm not going to go into the detail about the neural network because in the later half we will learn more about the neural network, and then we'll come back and revisit this diagram one more time when we learn more about the neural network. For other approaches, so we have a TensorFlow model. So for TensorFlow model, basically your input, right? So if you compare here, the neural network in ListNet, the input is only one query document pair, right? And then it's going to keep the score. But for the TensorFlow learn to rank model, the input of the neural network is multiple document, and the output is going to be full score or whatever the number of document you input. So basically, the network is trying to score multiple documents at the same time using the same network, right? And then the one that have the highest score would go to the top, and then the one with the lowest score is going to be on the bottom. So for this particular method, right, the interesting part is that your ranking will take many documents, right? So it's going to be so it's basically QD1, QD2, QD3, and then QD4, right? And then it's gonna give the score S1, S2, S3, S4. And then you can sort the order. So what is that? Is that it's gonna take this four document, it's only focused on this four document, and it could try its best to rank these four document among each other, right? So compared to the ListNet, right? ListNet care about the entire list, right? Because when you do the loss function, you look at all of the query document pair, and then you want to minimize the loss for every document query pair. But for TensorFlow, whatever you give it, it's going to minimize the local ranking. It's going to try only focus on um, for, right? You can modify the network to take 5 or 6 or 7, and then it's going to give you like 6, 5 or 7 score. So that is one way for um, listwise. Another one is to use BERT. BERT is bidirectional encoder representation for transformer. So for BERT, right, you have the query document pair, and then you use BERT as a encoder, right? Use BERT as an encoder, and then you give the score, and then you compare this score to the label, and then you compute the loss function. So this one is similar to ListNet, right? Because the network, right, actually receive one query document pair at a time, right? The input for BERT is one pair. But the difference is that the query document does not use the same feature extraction, right? It uses the transformer to convert like the sentence into some of the score. Right? So the query and the document, the position of the word matter. So it's going to be the different because it doesn't use the regular feature extraction. It doesn't use TF-IDF, doesn't use what else? It doesn't use like BM25 score. It have its own encoder inside, and it will produce the score for you. So this is how they use BERT in the learn to rank. Another one would be GAM, Neural Ranking Generalized Additive Model. And this one, it actually use multiple ranking, right? Based on other um, influence, right? For example, if you search hotel, right? For each hotel, it's going to have relevant score, it's going to have the price score, it's going to have the distance score. And for each one of these score, it's going to have a certain weight based on which device you search. And this is important because if you search using your computer, you are more likely for a hotel with a good price because you're not in a hurry, right? You are at home, you use your computer. So the weight for the price and the relevance is very high, right? But when you use a mobile phone, it may be that you are outside. You want to find a place to stay right away. So they just put more weight on the distance metric more. So the ranking will change depending on which device you use to search. So the same query can produce different results. So this is what they used for Agoda. In Agoda, they use this external influence, right? If you use like iPad, you use different phone, you use like laptop computer, the ranking is going to be different. But it's not going to be different by large because some of the hotel would be like very far apart, and even if you search using your computer, you may not want the far apart one. So the 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 learning, right? The function F1, F2, F3, right? For each of the um, for each of the feature will also have more impact than just the weight based on which device you use to search. So we haven't talked about evaluation, right? So the evaluation is basically the score of your model, right? If you come up with a model, is it good, is it bad? And for classification, what is the evaluation metric? Accuracy, right? What about linear regression? Is MSE, right? Means square error. For ranking, we also have these three evaluation metric for ranking. And the first two, actually the first one would not care so much about the order. But the last two is care about the order, right? So the order of the list that you give out, right, as the prediction. So what is map, right? Mean, average, precision. So in the map, right, in the map, right, we have many query. So for each query and a value k, we will look at the relevant document in top k result. So basically, if you give me a list of k document, I will just count how many documents are relevant, right? If I have relevant score, basically I can count any document that is not zero, right? If it's a binary, then yeah, I can just count the number of relevant document. So if the number is like, let's say 3/5, then you get 3/5, right? Basically in the K list you give, how many of them are relevant? That is the fraction. And that's it for the P, right? And then for the AP, the average precision. Now this average precision is defined on the query. So for this particular query, well, you give me a list, I just sum the precision of each rank, right? Of each rank. So let's say my list, I have top four, okay, top four. And I have D1, D2, D3, D4. And let's say that the relevance to be 0, 1, 1, 0, 1, 1. Okay. So if I calculate P of 3, right? PQ3, what is the value of PQ3? Right? If I have the data on the right side, what is the value of PQ3? So my query give me this ranking, and only the second spot is not relevant. So for PQ3, you look at the top three. And among the top three, there are two, so it's 2/3, right? What is PQ4? You get 3/4, right? What is PQ2? Is 1/2. What is PQ1? You get 1. right? Right. At the top result, in the top one result is relevant, so you get one. Now, what is the AP of this query? Right? The AP of this query is the weighted sum of the indicator variable times the precision at that ranking. So if we look at k equal to 1, right? K equal to 1 is the first document relevant? It yes, so you multiply by 1. What is the PQ1? PQ1 is 1. For k equal to 2, is the second document relevant? It's not relevant, so you multiply 0, right? So you don't care about the score at the top. For k equal to 3, you look at the top 3. At the third position, it is relevant, so you times 1. And what is the precision at 3? You get 2 over 3, right? And then k equal to 4. So 4 is relevant, so you multiply by 1. And then the precision at k equal to 4 is 3 over 4. And then you sum all this up, right? You sum all this up, so you get 1 plus 0 plus 2/3 plus 3/4 divided by the number of relevant document, which is number 3, right? There are 3 relevant document in your entire ranking, right? So this is the AP at Q, right? So we have the precision at top K for each top K, and then the average precision is the precision at that position times the indicator variable at that position, right? So this the indicator variable. It means that if the K document is relevant, this is 1. If the K document is not relevant, it is 0, right? That's why when K equal to 2, it becomes 0. Any question? Can you still follow? So this for one query, right? In your data set, you may have many query, so you just average them, right? Sum of the AP of all the query divided by the number of query. So that is your map score. Okay, let's do some example. So in my data set, I have 2 queries, Q1 and Q2. In the ground truth, Q1 related to ACE and Q2 related to BD. My prediction for my model, right? I have this ranking A, B, C, D, E. And for Q2, my ranking is B, A, D, C, right? So for the QD1, right? My number 1, 2, 3, 4, 5 is A, B, C, D, E. And what is my indicator at K? So A is relevant, right, from the ground truth. So indicator is 1. B is not relevant, right? So in the case it's 0, C is relevant, D is not relevant, E is relevant, right? Okay. So this is just from the ground truth, right? You give me the ranking, I just look at the ground truth and mark one where the document is related in the ground truth. And I compute the precision PQK. So if K equal to 1, what is my precision? 1, right? At K equal to 2, what is my precision? It's 1 over 2. For K equal to 3, what is my precision? 2 over 3. At K equal to 4, what is my precision? 2 over 4. And then K equal to 5, 3 over 5. So what is my AP for Q1? What is my AP for Q1? So basically, I just multiply these two, right? And then I sum everything up. So it's 1 plus 0 plus 2 over 3 plus 0 plus 3 over 5 divided by 3, right? 3 is the number of relevant, right? So that is AP for Q1. What is AP for Q2? What should be AP for Q2? Well, the bottom would be 2, right? There are 2 relevant documents. So what is the first term? It's 1, right? Because B is relevant. What is the second term? 0, right? Because A is not relevant. What about D? It's 2 over 3. And C, 0, right? So that is the AP of Q2. So the map score is the sum of these two divided by 2. Right? So if you want to have a high map score, what your ranking would look like? Right? What is the maximum map score you can get? What do you think would be the maximum of the map score? Right? If you have like a perfect ranking, it's going to be 1, right? Because the precision at every position would be 1, right? For example, if I have ACE, right? Then at A, my precision is 1. At C, my precision is 2 over 2. At E, my precision is 3 over 3. So the precision is always 1, right? And then the indicator would be 1. So basically, when you time everything, it's going to be 3, and then you divide it by the number of relevant document, then you will get 1. So the highest score for map would be 1. So what about this second example? What is the map score for Q1. This is for map score, just the average precision for Q1. Right. So Q1 related to ACE, and the ranking that I got is CEA. So what should be the AP score? Should be 1, right? So for the map score, it only care about having many relevant documents in the top of the list. That is all it care about, right? The ordering doesn't matter, right? You can swap ACE in any order. It's going to have the same score, right? So the map score, to have a high map score, it means that your ranking model actually put a lot of relevant document at the top of the list. That's all it matters. And what about Q2? Right. So you are missing one spot, right? So you have 1 plus 0 plus 2 over 3 divided by 2. Right. So that is the average precision for Q2. So that's the map score. The next one is okay, so interpretation of map, right? So map consider both order of the items, whether the relevant items are actually three, providing the comprehensive measure, right? So the map score of 1 would be the perfect ranking, and the score quarter to 0 would indicate poor performance. The next metric is MRR, mean reciprocal ranking. So the MRR equation is 1 over Q, right? 1 over the number of query times the sum 1 over rank I for each query. So what it means is that for each query, you get a ranking. It will look at the first rank that the document is relevant, right? If I give you a list like D1, D2, D3, D4, and the relevant score is and the relevant is like something like this, I will get 1 over 1 because the highest relevant score, the highest relevant document is at the rank 1. But if the ranking I got become something like this, then the highest relevant score is rank number 2. So I will get 1 over 2 for this instead. So it's only look at the top, like the most relevant document from your list, right? What is the highest from your list? And that is the score. And it's the reciprocal, right? It's the division. So you want the relevant score to be at the top, right? So for this measurement, right? For this measurement, right? If you have like uh something like this, right? If you have something like this for map score, the left side would have a higher map score, but the right side would have higher MRR because it's only care about the first rank that is relevant. So for example, right, I have my ranking, right, A, B, C, D, E for Q1. And then for Q2, I also have B, A, D, C. So what is the MRR for this? Right, so the MRR is I have two query, so it's 1/2. And then I have 1 over rank for each of the query. So for the first query, the highest relevant score or the highest relevant document is at the rank number 1. So I get 1. For Q2, the relevant score or the relevant document place rank 1. So I get 1/1. So I get MRR of 1. Right? So this is the perfect ranking. So it doesn't care about the rest. Right? As long as one relevant document is placed on the top, it's okay. Right? And what is the intuition behind this? Right? When you use Google search, right? When you use Google search, you only look at maybe top few results, right? And if the top few result is what you need, you don't care about the rest, right? If what you are looking for is at the first link, you click it, you get your answer, and then you don't have to care about the rest. So that is the intuition behind MRR score, right? Because from human perspective, we only need one answer. We don't need many correct answers. We only need one answer. And that one answer, we just want it to be high as possible in the ranking. So this one will also have MRR score of 1, right? Because C and D are both relevant. So they also have the same score. So MRR of 1 would indicate that the first relevant item is always at the top of the ranking. And then the 0 would suggest that the relevant tend to appear lower in the ranking. Right? So MRR is more straightforward than MAP. Right? So for both of these metrics, right, you only care about whether the document is relevant or not. You don't actually care about the relevant score or the actual ordering. So that's why we need one more metric that take into account the actual ranking. And that metric is called normalized discount cumulative gain. This metric have a lot of layers. So we'll go one by one. So the first we have CG called cumulative gain. And what this value do is you pick the number of rank, maybe top K, I don't know. And for your top K result, you add the relevant score together, right? So maybe top 3, you have D1, D2, D3, and then your relevant score would be, let's say 1, 1, 2, 0. And your CG for this particular query is going to be 3, right? Basically, you just sum up the relevant score of your top K result. But just summing up is not enough, because if you sum up, you actually put the importance on all the ranking equally. So we have to discount it, right? Discount means that you are not just sum the relevant score, but the further you go down the list, the score should decrease. So you divide it by log base 2 of I plus 1, right? So at rank 1, you basically just plus relevant score, right? Because log of 2 is 1. For rank 2, you have log 3. So log 3 is 1 point something. It's more than 1, basically, right? And this means that you are not just add the relevant score, but you just add a fraction of it. So based on the DCG, right, the ordering, right, matters, right? Because in this particular ranking, right, you have 1 plus 2 log 3, right? You have 1 plus 2 log 3. But for this one, you have 2 plus 1 log 3. And on the right side, right, basically you only lose a little bit of the score, right? Because the relevant score 1, you have a discount, but for 2, you get a full 2 point. But for the first ranking, right, for the 2 score, you don't get the full 2 score. You got discounted by log 3. So from the DCG perspective, not only you want your relevant document to place on top, but you also want the one with more relevant score to be higher. Because the more that you go down the list, the more discount you will get. And after you have DCG, right? So the DCG is basically your weighted sum of the relevant score of your ranking. How can we compute the actual score? We are going to look at the ideal, right? This I stands for ideal. So the ideal score, right, is the ranking sorted by relevant score from the ground truth. So what it means by that is that, for example, right, D1, D2, D3, let's say the relevant score is 210, right? And then the prediction is D2, D1, D3. So if the prediction is D2, D1, D3, the relevant score would be 120. Now to compute IDCG, right? To compute IDCG, you sort, right? Whatever the prediction you get, you sort them by the relevant score. So this is from the ground truth. You sort them by the relevant score, and then you compute the IDCG, right? And your final answer would be the DCG divided by IDCG. So it's basically compute your ranking with the perfect ranking, right? And the perfect ranking is by taking your ranking and then sorted by the Gauss, the value from the Gauss. So let's then look at some example. Might be easier to look at this example. So I have 5 documents, right, from D1 to D5, right? I have relevant score from 0 to 3. I have from 0 to 3. And my algorithm, my model, return this ranking. And then you have the relevant score of 32301. So what is the DCG? So the DCG for our would be 3, right, plus 2 over log 2 over log 3 plus 3 over log 4 plus 0 plus 1 over log 6. Right. So this is the DCG, right, from our answer from the prediction. So what about the ideal DCG? I think for this equation, I forgot to divide it by log I plus 1. It should have the same log I plus 1 at the bottom because it's also discounted. So for the ideal DCG, you actually have to sort this one to the perfect ranking. So what should be the perfect ranking? So the perfect ranking, right, you would have D1 and D3 at the top, followed by D2, followed by D5, and then followed by D4, right? You want the one with the score 3 to be at the top, and then 2 will go down, and then 1 and the 0, right? So you want to sort the score. So that is the perfect ranking, right? This one is perfect ranking. And from the perfect ranking, I can compute the ideal DCG, right? So for the perfect ranking, I have the relevant score of 3, 3, 2, 1, and then 0, right? So I'm gonna have 3 plus 3 over log 3 plus 2 over log 4 plus 1 over log 5 plus 0. So that is the ideal DCG. And finally, for my normalized, I just take the top divided by the bottom. So for this metric, right, for this metric, the ordering matter, right? So not only that you want the one with high relevance score to be on the top, you also want the relevance score to be in decreasing order as well. And it is important to note that for the ideal DCG, the perfect ranking that you compute must come from the prediction, right? If my database have D6 and it have relevance score of 2, but my algorithm only return 5, the D6 with the score will not appear in the ideal DCG. Only care about the result that we get and compare to what would be the best possible ranking, right? So it's compare the prediction with the best possible ranking based on the result of the prediction. So for the NDCG, again, one would indicate the perfect ranking. So all documents are ordered from the most to least relevant, and then 0 would be otherwise. So you have 3 metrics to score to compare the ranking model. So you can pick whichever one you think is most suitable for your problem, right? If you care about the ordering more, then you would use NDCG. If you only care about the top result, you can use MRR. So in the summary, right, our learn to rank algorithm, we want to rank the document based on the query, right? And then we have 3 approaches. The point-wise, basically you want to learn the score for each query document pair. For pair-wise, you also want to learn the score for each document pair, but the way that you compute the loss function, you take the difference between the 2 pair and compute the loss function. For list Y, you take a list and then you will compute the loss function. So the tree, you get a model that predict the score for one query pair, one query document pair. But the way that you calculate the loss function for point Y, for pair Y, for list Y is different. And then we have the key model. For the feature extraction, you have PageRank, you have IF, TF-IDF, or you have like BM75. And then for evaluation metric, you have MAP, you have MRR, you have normalized discount cumulative gain. And the application would be like search engine, recommendation system, advertisement, and so on. So that is all for the learning to rank algorithm. Um, it's not going to show up a lot in your work because most of the work that people done is not on the ranking side. Basically, most problems are in like prediction, classification. But I just want to show you that there is this type of problem that require a different way of thinking, right? Not just you have a feature, you have the answer, and then you get the answer. But you have to do some work before you get the answer. So any question so far? So I will not have the uh, assignment for learn to rank problem, but I just put the assignment for the classification. So make sure that you finish. I think it's due in like 2 or 3 weeks. Uh, yeah, it's due on the 29th. So it's still the same kickoff competition. So you have about 2 weeks to finish. It's a classification problem. So you can use decision tree or you can use any other method that you have learned from this course or from any other courses. So any question? So we will not have coding for this, because the most of the benchmark database is very large. They have like 1,000 query and then a million document. So you end up with like 1 GB of data for all of the document. So I will not show you the code for this, but I will upload some sample code that you want, that you can just um, take time to read on your own, but I will not just demo in the class. So don't forget about midterm exam. Next week is 30% of your grade. Oh, and I also post the past exam question in Mango Canvas, so you can take a look. But be mindful that the order of the topic may not be the same. Like some topic is covered before the midterm, some topic covered after the midterm is changed from year to year. So if some question you look at and then, oh, I haven't learned about this before, it means that it will appear in the final. Okay, so don't be alarmed. Any questions for this lecture or exam? So if not, then I will see you next week. So 8:30 be on time. So you have full 3 hours. Okay. See you.